Welcome to the Explainer. If you've ever felt completely overwhelmed trying to just blindly memorize hundreds of organic chemistry reactions, well, you are in the exact right place. Today, we're literally tearing up those flashcards and building a playbook. We're going to shift entirely away from rote memorization and focus on truly understanding the underlying rules that govern how these molecules actually behave. Okay, let's dive straight into our roadmap for today. We're journeying from the microscopic quantum level of molecular orbitals all the way up to macro reaction control. We'll be covering carbocations, classic reactions, the Hammett equation, and finally, tying it all together with one master mechanism.
Section 1. The true nature of electrophiles.
Before we even look at a single reaction, we really need to challenge some basic assumptions here. What really makes a molecule an electrophile? It's time to bust that classic textbook myth that they're always just things with a positive charge. Now sure, a positive charge definitely helps, but some positively charged molecules are actually terrible electrophiles because they're way too sterically crowded. On the flip side, completely neutral molecules can be incredibly powerful.
So the true hero of our story is actually the LUMO. That's the lowest unoccupied molecular orbital. The absolute foundation of an electrophile is simply having an accessible, empty orbital. You can really just think of it as the designated electron-accepting slot on a molecule.
Let's think about the actual quantum interaction for a second. A nucleophile brings its electrons to the party in its highest occupied molecular orbital, or HOMO. Now, for a reaction to actually happen, that HOMO must overlap with our electrophile's empty LUMO. A lower LUMO energy, combined with matching orbital symmetry, that creates a highly favorable overlap. And this perfectly explains why neutral molecules like boron trifluoride, or BF3, are incredibly powerful electrophiles. Boron only has 6 valence electrons, so it desperately wants 2 more, and it has an empty p orbital sitting right there at a nice low energy level.
To make this super easy to visualize, just remember this metaphor. Think of it as an empty parking spot waiting for an electron pair to move in. You don't need a positive charge to park a car, right? You just need a clearly marked, accessible, empty space. And that is exactly what a LUMO is.
Moving right along to Section 2, carbocations, stability and rearrangements.
All right, so now that we know where electrons want to park, we have to navigate the shifting landscapes they encounter along the way. Carbocations act as our electrons' first major obstacle. As a quick refresher, a carbocation is a carbon atom with only 6 electrons carrying a positive charge. Think about a methyl carbocation. It has 0 adjacent sigma bonds to help it out, making it incredibly unstable. But as you add adjacent carbon-carbon or carbon-hydrogen bonds, creating secondary and tertiary carbocations, the stability dramatically increases. Why? It's all because of hyperconjugation. Those adjacent sigma bonds actively donate just a little bit of their electron density into the empty p orbital. They are essentially sharing the burden of that positive charge.
But here's the catch. Unstable carbocations don't just wait around to be rescued, they actively seek stability. So here is an absolutely critical rule you must apply. Whenever a primary or secondary carbocation forms, you have to stop and ask yourself, can a 1-2 shift give a more stable cation? Check the adjacent carbons. Is there a hydrogen or an alkyl group that could migrate over? If the answer is yes, that molecule is going to magically break the standard rules, shift its atoms around, and upgrade itself to a tertiary cation. And for us, that means a completely different rearrangement product is highly likely to form.
Section 3. Classic electrophilic reactions.
Let's take all this to the classic battlegrounds where these rules are put to the ultimate test. And this brilliantly illustrates the 2 major behaviors we see in organic chemistry. First, consider Markovnikov addition on alkenes. The alkene's pi bond attacks an electrophile, forming the most stable carbocation intermediate possible, just like we were talking about. And that dictates exactly where the final bromine attaches. But contrast this with electrophilic aromatic substitution, or EAS. Benzene is highly stable. So instead of just adding a group and destroying that beautiful aromatic stability forever, it temporarily breaks aromaticity to attack the electrophile, forms an intermediate, and then smartly kicks out a proton to restore the stable ring. It substitutes rather than adds.
Which brings us to Section 4, quantifying with the Hammett equation.
We've spent some time on the qualitative rules, but now let's pull back the curtain on the strict mathematical laws governing these electronic effects. Enter the Hammett equation. It states that the log of the reaction rate ratio is equal to sigma times rho. Now, I know it looks a bit abstract, but it's an incredibly powerful predictive tool. In short, sigma represents a specific substituent's power to push or pull electrons, while rho measures the overall reaction sensitivity to those specific electronic changes.
Let's demystify this math a bit. Look at how these sigma values stack up. The electron withdrawing groups, we can call them the stealers, like the nitro group, have positive sigma values. They are actively pulling electron density away from the ring. Conversely, the electron donating groups, the sharers, like a methyl group, have negative sigma values because they are actively pushing electron density into the system. By combining these values, chemists can predict exactly how fast a reaction will go without having to run every single experiment in the lab.
Section 5. Hard, soft, fast, or stable.
We are now transitioning to the high-level macro control mechanisms that dictate exactly which product forms in a complex system. First up, let's break down hard-soft acid-base, or HSAB theory. Hard electrophiles are small, they have high charge density, and they really don't distort easily. Soft electrophiles, on the other hand, are large, highly polarizable, and sort of diffuse. The golden rule to remember here is like reacts best with like. Hard electrophiles prefer to match with hard nucleophiles for tight, direct interactions. Meanwhile, soft electrophiles prefer soft nucleophiles for more diffuse covalent-style orbital overlaps.
Next, we absolutely have to look at the reaction conditions. So the crucial point here is that simply changing the temperature of your flask can completely alter a reaction's end product. Under kinetic control, meaning low temperatures and short times, the reaction is irreversible, and the product that forms the absolute fastest dominates. But switch to thermodynamic control, higher temperatures and longer times, and the reaction becomes reversible. It essentially goes back and forth until the system inevitably settles on the most stable possible product, completely regardless of how fast it formed initially.
And finally, Section 6, the master mechanism. All right, it's time for the climax of our explainer. Everything we've just learned, from identifying those empty LUMO parking spots and avoiding carbocation rearrangements, to understanding directing groups and thermodynamic stability, it all comes together right here. This is how we execute complex chemical syntheses, like the famous Friedel-Crafts acylation.
Let's move through this and see exactly how it builds in a beautifully clean, logical sequence. Step 1. We generate our super electrophile. Aluminum chloride acts as a Lewis acid to pull a chloride right off an acyl chloride, creating a highly reactive yet resonant stabilized acylium ion. Step 2. The benzene ring acts as the nucleophile. Its pi electrons attack the acylium ion, temporarily breaking its own aromaticity to form the uranium ion intermediate. Step 3. A proton is lost. The electrons fall perfectly back into place, aromaticity is instantly restored, and boom! We are left with our stable final product, an aroketone. Think about that. We've moved from the simple concept of an empty parking spot all the way to engineering multi-step organic synthesis. You now understand the playbook. So I'll leave you with this final provocative thought. How will you use these predictive rules to design a molecule of your own? Because once you stop merely memorizing and start actively understanding these fundamental rules, the chemical pathways are entirely yours to design. Thanks for joining us on The Explainer.